A signal rises from the dark. Not a voice, not debris, not wreckage. A pattern. 3 descending sweeps on a deep-sea scan, perfectly geometric, buried nearly 4,000 meters below the surface. And within weeks, the official search zone for MH370 quietly shifts. Hard cut, coordinates flash, map redraw. Why? What did they see? Who saw it first? And why did the grid move only after deep-sea drones entered the water? Because this wasn't a random fishing trawler's sonar. It was a fleet of autonomous deep-sea vehicles, launched as part of China's expanding oceanographic program, mapping one of the most remote stretches of the southern Indian Ocean. A place defined by absence. No islands, no shipping lanes, no witnesses, just pressure, darkness, and time. The anomaly appears as a hard-edged return, unlike sediment drift, unlike rock scatter, too angular, too isolated. Within days, satellite maps begin circulating internally. Within weeks, the public search box shifts hundreds of kilometers. Coincidence or correlation? And if correlation, what exactly did those drones detect? Because moving a search zone that large isn't trivial. It costs millions. It redirects ships. It reshapes international coordination. You don't do that on a hunch. You do it when something changes the model. Aviation analysts later describe it carefully. New technical data prompted re-evaluation. New data. From where? Above the sky or beneath the ocean? And here's the unsettling part. The drones weren't even looking for an aircraft. They were mapping seabed topography, measuring tectonic formations, cataloging mineral structures. Yet something in that scan resembled order inside chaos, a geometry in the abyss. And when geometry appears where only randomness is expected, investigators pay attention. Because if an aircraft came down at high velocity, fragmented across kilometers, then why would there be a single consolidated echo? Unless the aircraft reached the water differently than previously modeled, or the debris field behaved differently at depth, or the search assumptions from the very beginning were slightly wrong. And that possibility? That's seismic. But before we go further, before we descend into pressure, algorithms, and satellite arcs, let's do something important. If you're here because you want more than headlines, if you're here because you believe the ocean still holds answers, then this channel is your investigation room. We examine anomalies without sensationalism. We separate models from speculation. We follow data, even when it leads into uncomfortable territory. So if you value that kind of inquiry, consider subscribing. Like the video if you want deeper dives like this. And tell me in the comments, do you believe the search zone moved because of new ocean data, or because earlier assumptions were flawed? Your insights shape what we investigate next. Now, let's rewind. Because to understand why a deep-sea drone scan matters, you have to understand how the search for MH370 was built in the first place, and why its final arc became one of the most mathematically debated corridors in aviation history. It begins on a routine overnight flight. A wide-body jet departs Southeast Asia just after midnight. Clear weather, normal climb, standard routing toward northern airspace, passengers asleep, cabin lights dimmed. At 38,000 feet, everything appears ordinary. Then, a routine radio handoff, a calm sign-off, and silence. No distress call, no transponder reply, no mayday. Within minutes, civilian radar loses the aircraft. Military radar tracks an unidentified return turning west, a turn that was never scheduled, a turn that should not have happened. For nearly an hour, primary radar detects an object crossing back over the peninsula, then disappearing toward the open ocean. After that, nothing visible, no radar track, no eyewitness reports, just absence. But the aircraft wasn't completely gone, because above the Earth, 36,000 kilometers up, a communication satellite was still exchanging automated handshake signals. Not voice, not data, just hourly electronic pings. Each ping confirmed the aircraft's satellite terminal was powered, and each ping created a mathematical arc, a ring on the Earth's surface showing where the aircraft could be at that moment. Arc 1, Arc 2, Arc 3, 7 in total. These arcs stretched like invisible ripples across the Indian Ocean. And here's where it becomes technical. Each handshake contained two critical measurements: burst timing offset, how long the signal took to travel; burst frequency offset, slight Doppler shifts caused by movement relative to the satellite. Timing told investigators distance. Frequency hinted at direction and speed. When analysts modeled the data, two possibilities emerged: a northern corridor, a southern corridor, one toward Central Asia, the other into the vast emptiness of the southern Indian Ocean. One passed over land, where radar would likely detect it. The other passed over almost nothing. Sparse radar. No witnesses, no airports, just water. By the seventh arc, roughly 7 hours after departure, the satellite handshake ended. No final distress signal, just a final automated ping. And then, silence. Investigators ruled out the northern route. Radar data from multiple nations showed no unidentified aircraft crossing that corridor, so attention shifted south. But south isn't a point. It's a corridor thousands of kilometers long. Imagine drawing a curved line across one of the most remote oceans on Earth. Now imagine trying to find a debris field somewhere along it, at depths reaching 6,000 meters. That's the scale. Search vessels deployed, sonar arrays scanned, autonomous underwater vehicles mapped grid after grid. Months passed, then years. Pieces of debris eventually washed ashore on distant coastlines, confirming the aircraft likely ended in the southern Indian Ocean. But debris drift modeling is imprecise. Ocean currents shift, wind alters trajectories, time distorts certainty. The official underwater search zone became a narrow segment of the seventh arc, chosen using satellite Doppler modeling and fuel endurance estimates. It was the most statistically probable endpoint, not certainty, probability, and that distinction matters. Because if the model assumptions were even slightly off, speed, altitude, glide characteristics, then the projected impact zone could shift hundreds of kilometers. Which brings us back to the anomaly. Because when China's deep-sea mapping drones began surveying adjacent seabed territory years later, they were operating near the edge of the original search box, near, but not inside it. And shortly after those missions concluded, the search zone moved. Not randomly, strategically. Further north along the arc. Why adjust a model years after exhaustive scanning? What variable changed? Was it satellite reinterpretation, ocean drift recalculation, or something seen on the ocean floor? In aviation investigations, models evolve, but they rarely pivot without trigger data. So in the next chapter, we descend, not into speculation, but into mechanism. Because to understand why deep-sea drones matter, you need to understand what they can actually see, and how the ocean floor preserves, or erases, evidence. 4,000 meters below the surface, sunlight does not exist. Pressure exceeds 400 times what you feel at sea level. Water temperature hovers just above freezing. Sediment falls like slow, perpetual snow. And in that darkness, machines move, not submarines with crews. Autonomous underwater vehicles, UVs unmanned, pre-programmed, quiet. They don't see the way humans do. They paint with sound. Here's how it works. An AUV travels roughly 50 to 100 meters above the seabed. From its sides, it emits acoustic pulses, high-frequency sonar waves. Those waves strike the ocean floor. They bounce back. The time it takes for the echo to return calculates distance. The strength of the echo reveals texture and shape. Soft sediment absorbs sound. Rock reflects it sharply. Metal? Metal reflects differently, more intensely, more cleanly, often with shadowing behind it. On sonar imagery, debris casts a signature. A bright return with a dark acoustic shadow. Geometry becomes visible. Straight lines stand out in a world of randomness. That's why sonar is so effective in wreck searches. It doesn't care about light, it cares about structure. Now imagine you are analyzing terabytes of seabed scans, millions of square meters, mostly sediment ridges, occasional rock outcrops. Then, a shape appears. angular, distinct from natural formations. Is it wreckage or just a geological anomaly? Because here's the problem. At extreme depths, impact physics behave differently than surface assumptions. If an aircraft struck the ocean at high speed, fragmented violently, and sank, debris would likely scatter across kilometers. But if descent occurred at a lower vertical velocity, perhaps gliding, the fuselage could remain more consolidated. The breakup pattern would change. And if the seabed below is relatively flat and sediment-heavy, wreckage can partially bury itself over time. Sediment accumulation rates at those depths can range from millimeters to centimeters per year. In a decade, components could be partially concealed. Sonar would still detect mass, but outlines blur. And here's another variable: topography. The southern Indian Ocean floor is not a smooth plain. It contains fracture zones, undersea ridges, volcanic features. If wreckage fell along a slope, debris could migrate downslope over time. Gravity doesn't stop underwater, it slows. So when China's deep-sea drones conducted broad geological mapping missions, they weren't scanning narrowly like search vessels do. They were scanning wide, mapping corridors adjacent to the previously searched grid. And wide area mapping increases probability of incidental discovery. But discovery isn't confirmation. Because sonar anomalies must be verified visually, that requires a second deployment, often a remotely operated vehicle with cameras. Did that happen? There's no public confirmation, only timing. Drone surveys completed, internal analysis performed. Then, months later, the official search zone proposal shifts north along the arc. Coincidence? Possibly. But in deep-sea operations, repositioning is expensive. You don't redirect multinational search efforts without technical justification, unless the sonar data suggested the probability map needed recalibration. Now consider something subtle. If a new seabed anomaly appears slightly north of the original grid, and if that anomaly aligns with revised fuel endurance models, then two independent datasets converge: sonar geometry plus satellite math. And when independent systems agree, confidence increases. But confidence is not proof, because sonar images are ambiguous. Natural basalt formations can mimic linear edges. Submarine landslides can create debris-like patterns. Even manganese nodules can cluster into shapes that resemble wreckage under certain acoustic frequencies. So the key question becomes, was the anomaly strong enough to trigger remodeling? Or was the satellite data itself quietly reinterpreted first, and the drone findings simply coincidental? Which came first, the seabed geometry or the recalculated arc? Because the order matters. If the drone data came first, then something tangible may exist below. If the arc recalculation came first, then the drones may simply have been operating near a statistically adjusted corridor. Same movement, different implications. There's one more layer. Deep-sea missions often collect raw data not immediately released publicly: bathymetric grids, reflectivity charts, sub-bottom profiles. In some cases, data is archived within research institutions before formal publication. So it's entirely possible that an anomaly was logged, cataloged, but not yet verified, which means the ocean may already know more than we do, and we wouldn't see it. Not yet. In the next chapter, we step away from models, because behind sonar returns and satellite arcs were families waiting, and the human dimension of this search, often overshadowed by math, may explain why even small anomalies trigger massive decisions. Long before deep-sea drones scanned the ocean floor, before models were recalculated, before grids shifted, there was a departure gate. Families hugging goodbye, a delayed boarding call, the ordinary choreography of travel. No one there knew they were participating in history. 7 hours later, phones began lighting up. Is it true? Have you heard anything? Maybe it's just a communications issue. Because at first, that's what it was described as: a lost contact, a routine anomaly, a temporary disappearance from radar. But as hours stretched into a full day, language changed. Missing aircraft, then days, then weeks, and the word nobody wanted to say began echoing in private conversations. Gone. Families gathered in hotel conference rooms converted into briefing centers, projectors, maps, timelines, arcs drawn across oceans, experts explaining Doppler shifts and satellite pings. Try to imagine that moment. You're told your loved one may be somewhere along a curved line thousands of kilometers long. Not a location, a probability corridor. How do you grieve a probability? How do you hope inside an arc? For years, every announcement mattered. A floating object sighted by satellite imagery. A fragment washing ashore on a distant beach. A sonar contact. Each time, headlines surged. Each time, expectations rose. And often, each time, they fell. The human cost of uncertainty is different from confirmed loss. It lingers. It suspends closure. No confirmed wreck site means no final image. No black box recovery means no definitive explanation. No coordinates means no memorial at the place of rest. Just ocean. Endless, indifferent ocean. And that's why small technical shifts matter so much. When a search zone moves, it is not just a logistical adjustment. It reopens hope. And hope can be both sustaining and painful. Because if the zone shifts north, it implies the previous search may have missed something, which implies the aircraft may still be waiting in a different patch of seabed, which implies the story is not finished. For families, that matters. For investigators, it demands rigor. Because moving a search grid without strong justification risks eroding trust. And trust, in long investigations, is fragile. Now consider this. Years after official underwater searches concluded, private initiatives proposed renewed operations, new funding, new modeling, new confidence in a slightly adjusted corridor. Why? Because statistical refinement suggested the aircraft's final descent may not have been uncontrolled freefall. Some analyses proposed a possible glide, a controlled descent attempt. If true, the impact zone narrows. If false, debris disperses wider. The difference between chaos and pattern. A drone mission near the Ark. A revised probability corridor. A renewed proposal to search. 3 threads crossing. Coincidence? Maybe. But in unresolved investigations, coincidences demand inspection. Because somewhere beneath thousands of meters of water and sediment, there may be a cockpit voice recorder still holding its final seconds. There may be flight data waiting to confirm or dismantle every prevailing theory. There may be answers that change how future aircraft are tracked, monitored, safeguarded. This is no longer just about one flight. It's about systems, transparency, global coordination, and the limits of technology in the face of vastness. In the next chapter, we confront the branching paths, because there are at least 3 plausible explanations for why the search zone shifted, each supported by different data, each leading to different conclusions, and only one of them suggests that deep-sea drones may have already glimpsed something extraordinary. The search zone moved. That is fact. Why it moved, that is interpretation. There are 3 primary explanations, each plausible, each incomplete, each carrying very different implications. Let's examine them. Theory 1. Satellite recalibration. The simplest explanation is this. The move had nothing to do with deep-sea drones. It was math. Years after the disappearance, independent analysts re-examined the burst frequency offset data, the Doppler shifts embedded in the satellite handshake signals, small refinements in assumed climb rate, slight adjustments in end-of-flight descent modeling, updated wind field reconstructions. If you alter any one of those inputs, even marginally, the final arc intersection point shifts. Not dramatically, but enough. Models suggested the aircraft's final descent may have occurred slightly north of the originally searched grid. If true, then the initial underwater search, though extensive, may have scanned the wrong segment of seabed. Pros: based on measurable telemetry, transparent modeling process, supported by some independent aviation analysts. Cons: still dependent on assumptions about aircraft behavior in final minutes. No direct physical evidence from seabed. In this version of events, the drones were irrelevant. The arc moved because the math matured. Clean, procedural, understandable. But that's only one path. Theory 2. Ocean drift reanalysis. Fragments confirmed to be from the aircraft washed ashore on distant coastlines. Those drift patterns were back-modeled using ocean current simulations. But ocean modeling is imperfect. Currents change seasonally. Eddies form unpredictably. Wind-driven surface drift differs from subsurface flow. New computational simulations suggested debris origins slightly north of the original box. If debris started further north, then the impact site likely did too. This theory doesn't rely on satellite reinterpretation. It relies on oceanography. Pros, anchored in real recovered debris, uses improved current datasets and longer drift timelines. Cons. Ocean drift modeling carries large error margins. Surface debris may not represent main wreckage position. In this version, the drones again are incidental. The zone shifted because the sea told a different story. But then, there's Theory 3. Theory 3. Seabed anomaly. Detection. This is the most provocative and the most uncertain. China's deep-sea mapping missions operated near, but just outside, the previously searched grid. Wide-area geological surveys, high-resolution side-scan sonar, sub-bottom profiling. If those missions logged a sonar anomaly consistent with artificial structure, even tentatively, that data could prompt quiet consultation among analysts. Not a public declaration, not a press conference, just technical reassessment. If sonar detected something that matched mass expectations for large wreckage components, and if that location aligned reasonably with revised ARC modeling, then two independent systems would converge. That convergence could justify shifting the official search proposal north. Pros: physical signal from seabed, independent from satellite assumptions, explains timing correlation between drone surveys and zone movement. Cons: no publicly confirmed anomaly released. Sonar artifacts are common and often misleading. No visual confirmation disclosed. This theory hinges on something unverified, not proven, not denied, just possible. Now ask yourself, if the shift were purely mathematical, why did it occur after drone surveys? If it were purely ocean drift modeling, why did earlier years of analysis not yield the same adjustment? And if it were seabed detection, why no announcement? Because in international investigations, data sharing is layered. Technical findings may circulate privately long before public acknowledgement, or there may have been nothing definitive at all. Correlation does not equal causation. Timing does not equal proof. But timing invites scrutiny. And here's the deeper question. Which explanation requires the fewest new assumptions? Satellite recalibration, drift modeling, or a quiet sonar anomaly? Each pathway leads to a different ending. One suggests the aircraft lies just beyond previously searched waters. One suggests ocean dynamics misled analysts. One suggests the ocean floor may already hold the answer, logged in a dataset not yet fully disclosed. In the next chapter, we introduce something new, because a later reanalysis proposed a descent profile that changes everything. Not chaotic spiral, not fuel-starved freefall, but a potential controlled glide. And if that model holds, the impact point narrows dramatically, which would make the zone shift not just logical, but inevitable. Years after the initial search ended, a quiet reanalysis emerged. Not a headline, not a press conference, a modeling refinement. It proposed something subtle, but transformative. What if the aircraft did not plunge uncontrolled in its final seconds? What if, after fuel exhaustion, the engines flamed out, and the aircraft entered a glide? Modern wide-body jets, even without power, can glide for significant distances, depending on altitude and trim. If the nose was level, if flight controls remained responsive, if no catastrophic breakup occurred mid-air, then the descent would not be vertical chaos. It would be a curve, and that curve shifts the impact zone, not randomly, predictably. Modelers recalculated fuel exhaustion altitude, glide ratio, wind vectors, descent oscillation. The new simulations suggested a point slightly north of the previously scanned seabed, a narrower patch along the 7th arc, which, Coincidentally, overlapped regions later mapped by deep-sea drones. Coincidence? Maybe. But when satellite telemetry, drift analysis, and glide modeling all begin clustering around a tighter corridor, probability sharpens. And that is what may have happened. Not discovery, not confirmation. Convergence. If the aircraft glided, even briefly, someone may have been conscious in those final minutes. That possibility changes the human dimension, but it remains unproven. Flight data recorders would answer it. They remain unrecovered, and so we're left here. A revised arc, a mapped seabed, a drone anomaly, possibly nothing, possibly something. A search zone that moved. The ocean still holds its silence, but silence is not emptiness. It is pressure. It is sediment. It is data waiting to be read correctly. So the question is no longer just, where is the aircraft? It becomes, have we already looked at it without recognizing what we were seeing? Because if a sonar image was logged and dismissed, if a corridor was nearly correct but slightly offset, if the answer lies just beyond a previously scanned grid, then history may record this not as an unsolvable mystery, but as a problem of inches and oceans. The search zone moved. Was it mathematics evolving? Ocean currents correcting the narrative? Or deep-sea drones quietly revealing a shape in the dark? The next expedition may decide. Until then, the southern Indian Ocean keeps its geometry, and somewhere beneath 4 kilometers of water, the final seconds of a flight may still be waiting.